Hello, and welcome to episode number 20 of CS350 Online. I'm your host, as always, Leslie Eisted, and on today's episode, we're going to start a new topic, and that is the topic of file systems. But before we do that, let's look at our OS of the day. So today's OS is Windows. We have actually finally reached the day where we can talk about it. And this operating system, the first version, Windows 1.0, was released on November 20th, 1985. So that means that Windows is pretty much 35 years old. It's a very old operating system. Okay, it's not that old. Windows 1.0 and a number of other versions of Windows were actually just extensions of DOS. So like Apple's operating systems, where they kind of have two distinct eras that represent completely different kinds of operating systems, Windows actually has the same. And the first era is the DOS extension era, and that started with Windows 1.0, which was really just made to compete with Mac OS because Bill Gates really felt like Apple was offering a product that people wanted. They built it to be an extension of DOS that offered a simple graphical environment where you could point and click. But it was very limited, and it wasn't something where you didn't turn your computer on and it auto-booted into Windows 1. You actually had to manually start it. In fact, it was pretty unusual to have things boot into Windows until I want to say maybe half of the Windows 3.1 installs would auto-boot into Windows, and the other half of them you actually had to manually start Windows 3.1 on your own. So what it did is it had very limited multitasking, and it wasn't multitasking from the perspective of the user's programs being able to have multiple threads, but it was simply for the message passing loop for the actual user environment. And then they didn't permit a lot of the traditional windowing behaviors. So they only permitted, aside from the welcome screen, they only permitted tiled windows. They didn't actually permit, generally speaking, overlapping windows that you could drag and have like cascades. So that was Windows 1. There was a Windows 2. It's not worth mentioning. The next one worth mentioning is actually Windows 3.1 or 3.11, as it's also a very similar one. And this is actually Microsoft's last 16-bit operating system, and it's probably one of their most popular from the previous era. And it did actually support multitasking in the form of cooperative concurrency. So you remember that is concurrency where in order to change which thread is running, you either have to block, terminate, or voluntarily give up the CPU via a yield. So if you didn't write your application in that way, then there would be no context switching. Now, Windows 3.1 did also offer virtual memory, and if memory serves me, it was actually segmented virtual memory. It's been a long time since I looked at its virtual memory. And surprisingly, it didn't actually become a problem. So we know that segmentation actually causes fragmentation problems. And it wasn't a problem for Windows 3.1. And the reason kind of why it wasn't is because you're still looking at an era where people weren't actually thinking about the fact that they could run multiple programs at the same time. So I actually spend a lot of time when I was younger using Windows 3.1. It's one of my favorites, actually. I have a VM around of it where I can play Windows 3.1 games in Windows 3.1. It's fun to play them in Windows 3.1. But when you're using the Windows 3.1 interface, and I will show you it because many of you, I'm assuming, haven't actually seen it before, it's not easy to switch between the programs that you have running. So if you open Netscape Navigator, which was the browser at the time, and then you open, say, WordPerfect, it wasn't actually easy to switch between those two programs. And I think it wasn't so much that that's the way Microsoft designed it. It was just that nobody was thinking about that kind of behavior back then because there wasn't enough memory to really support that effectively. There wasn't enough processing power. So it's not that it couldn't be done. It's just that it wasn't it wasn't in the consumer's mindset that they could do it, and so Microsoft didn't necessarily support that as obviously as they did in later operating systems. Now, Windows 3.1 is long since deprecated, but it's actually still used today. And the reason why it's still used today is because it's very tiny. Windows 3.1, the last time I installed it, it was on 4 floppy disks, 4 3.5-inch floppy disks, and each of those floppy disks stores 1.5 megabytes, well, 1.55. So you're looking at, so 4 times that, you're looking at less than 10 megabytes. And today, that's actually a really nice size for an embedded operating system. You can put that on a chip because chip memory is very cheap these days. And now you've got an operating system in your hardware. And where you'll see this used is things like airplane entertainment systems, POS devices, and so on and so forth, that are looking to actually have the operating system be a part of hardware. And again, Windows 3.1 is still just an extension of DOS. It is built on top of DOS, as are Windows 95, Windows 98, and Windows ME, with ME actually being the last of Microsoft's true DOS-based operating systems. Now, some of these operating systems actually achieved quite a bit of success, and some of them were pretty epic failures. So Windows 95 was really popular, but it was super, super buggy. And so I want to say that Windows 95 was a bit of a failure, but Windows 98 was actually quite a bit of a success. Windows ME, that was a failure. That actually was an incredibly buggy version of Windows. Now, at the same time, throughout the 90s, Microsoft was also developing a second version of their operating systems, and these were not necessarily meant for consumers. They were meant for commercial applications. And this is the NT family, and they started developing this around 93. And the NT family, it started out with like Windows NT1 and NT2 and NT3 and NT4. I think I started using Windows NT around version 3, but I don't quite remember. But the NT family of operating systems does not, it's not built on DOS. It's not built on the functions of DOS. It wasn't meant to be compatible with DOS or anything like that. It is its own completely separate operating system. And as part of that, it does full 32-bit virtual addressing. It was the first one to use it, of Windows that is. And now, of course, it uses 48 bits. And it did preemptive multitasking because consumers may not see a need for that, but certainly commercial applications did. And then what ended up happening is after Windows ME, that whole DOS era ended, and the NT family actually became both the commercial and the consumer one. So you're seeing Windows 2000, which came out after Windows ME, and you're looking at XP, Vista, 7, 8, 9, 10. All of those are based on the NT series. And you might be like, well, how are they not based on DOS? I can open up a DOS terminal. And it's actually just an emulator, and it's not quite pure DOS environment. And the only reason why they are offering you that environment is for backwards compatibility, because there are many companies that have built applications on top of DOS, and they want to make sure that those applications still run. And that's actually one of the interesting features about the NT family. I mean, if you have Windows 10 in front of you, and my little Surface here to the side actually runs Windows 10. But not that I use it very often. If you try to run an older application, like one of my favorite games of all time is Red Alert 2 and Yuri's Revenge, and I can't just run them natively in Windows 10, so you actually have to run them in an emulated mode. So you kind of like right click on the application and you'll say run as Windows 3.1 or run as Windows 95. So they've actually built in emulation of their previous operating systems into the NT support for the purposes of making sure that companies have that backwards compatibility for applications they wrote 25 years ago. And that's actually really important, because if you want to convince a company to switch to your operating system or upgrade their operating system, you really need to convince them that none of their previous programs or their workflows are going to break. Because if you break their workflows, you're actually going to be costing them more than just the licensing fees for the new operating system. You're costing them time and manpower that they don't want to spend in retraining and fixing and so on. So you've got to convince them it works. And so Windows NT actually has a lot of backwards compatibility built in. Now, some interesting things about Windows versus macOS is that macOS has a very consistent look and feel from 1984 to today, but Windows has not had a consistent look and feel. It feels like they're constantly trying to innovate, and sometimes it's successful and sometimes it's not successful. So this is actually, and I know it's very blocky, but keep in mind this is a really old, this is 1985. This is Windows 1.0. And you'll notice that aside from this welcome window here, all of the other windows are actually tiled and not overlapping. You could have them open. They were tiled. They were tiled. They couldn't overlap. This is Windows 3.1, and it kind of looks a lot. It's very similar to Windows 1. I have used Windows 1, but it's been a long, long time. You could have the windows overlapping, but it was kind of weird in the sense that when you minimize something, how do you bring it back up again? So there's minimize and maximize buttons there. So you actually use more of an overlapping strategy to switch between programs, and that was kind of a weird thing. But Windows 3.1 was a lot of fun to use. Some of the biggest problems with Windows 3.1 was driver support. People would write programs, and they would be written and they'd have to support very specific kinds of graphics or sound cards. And if you didn't have those specific graphics or sound cards, then it simply wouldn't run. So the level of abstraction here wasn't as good as it was today. Still really fun in OS. So then you go from Windows 3.1 to, this is of course Windows 10. Windows 95 and up, I feel all have a very similar look and feel because they have the bar at the bottom. They have a start menu, which is a very familiar concept to us. Now Windows 10 and 8, they have Cortana, which of course everybody disables like the second they turn it on. And then you've got this handy bar down here with any kind of shortcuts to battery life and so on. Now, with some of the later versions of Windows, because Microsoft has started releasing these tablets, they actually have two separate UIs built in. So there's kind of, and I don't remember the name of it off the top of my head, but you've got, you're going to have the standard desktop style environment. And then I think it's called Metro. You've got kind of like a tablet interface. And one of my biggest complaints about the Windows 10 UI is that some of the settings have to be accessed through the Metro interface, and some of the settings have to be accessed through the standard desktop interface. And some of them can be accessed by both, and they're displayed differently. And I find that very bizarre, and I think it's very confusing for users. So, I mean, there are successes to this, and there's also some negatives to this. I don't, generally speaking, use Windows. Coding in Windows is not fun for me. All right, so before we start back into our new topic, what I would like to talk about first is I left you with a sample problem from the devices in I/O segment. And I would like to actually take that up. So let's find it. So this is the disk I/O problem. Here it is. And it's saying that, you know, suppose that a server has a single disk drive and one single core processor. You have a total of K processes are running, and each process, if it were running alone in the system, will request to retrieve one 4 kilobyte block of data every 5 milliseconds. So it's going to, think of it this way. You've got a process that's going to do 5 milliseconds of compute, and then it's going to make an I/O request. And while it's making that I/O request, it can't continue computing because it needs the work, or it needs the data from the disk in order to continue. So then there's a description of the disk saying that it has 2 to the power of 10 tracks, total capacity of 128 megabytes. That's the total disk capacity. And what we want to know is, if there's only one process, what is the CPU utilization? Now, what is CPU utilization? Well, CPU utilization is what percentage of the time is the CPU actually computing something. Now, if we make the assumption that the data transfers are going to happen via DMA, what we're really asking is what percentage of the time is the CPU not idle, that is not waiting for the disk to return. So let's actually start this. There's two parts to this problem. The first is with the process as being 1. So I'm going to open up OneNote here and we'll make it a little smaller. Of course, that didn't do what I want. Okay, there we go. Get my pen here. Okay, so the way that you should attack this problem is to start by actually computing how long it takes to do the service request. So we're going to start by looking at what is the maximum rotational latency. So the maximum rotational latency, and there is a guide, by the way, on Piazza that actually lists all of these formulas and some examples, and I recommend you take a look at them. So the maximum rotational latency is actually going to work out to be 10 milliseconds because we do 100 rotations per second. So our maximum rotational latency is 10 milliseconds. And then we're going to need to compute the seek time. Now, we don't know anything about what track we are on right now or what sector we're on right now. We know nothing about the drive's position. When you know nothing about the current position of the disk and you don't know where the disk needs to go to, you should always make sure that you're using the average seek and the average rotational latency. Now, the average seek is actually given in the question, but if it's not given, just take the maximum and divide it by 2. And yes, there's a reason for why it's the maximum divided by 2. We're not going to get into that. It's a big expected cost equation. All right, so we've got 5 milliseconds as our average seek. Now, we haven't actually computed our average rotational latency, but we can do that off the top of our heads here. We'll assume that the average rotational latency is going to be half of the max. So we'll say it's 5 milliseconds. Okay, so that's 2 of the 3 components of our cost. Remember that our cost is the rotational latency plus the seek, and then the third component is the actual transfer time. So how do we compute the transfer time here? So in order to compute the transfer time, we need to figure out what percentage of the track is this 4 kilobyte block of data corresponding to. So we need to figure that out. So we'll start by figuring out how much data is actually stored in a track. So we have 2 to the 10 tracks. And our disk capacity, apologize for the messy writing here. Our disk capacity is 2 to the power of 27. So that means there are 2 to the 27 divided by 2 to the 10 bytes per track, which of course is equal to 2 to the 17. Okay, knowing that there's 2 to the 17 bytes per track, now we need to know how many blocks per track are there. Now, you'll notice that when we talked about disk drives before, we talked about sectors. Sectors are typically 512 bytes, and disks usually do sector-based addressing. And we'll talk more about that in this episode and the next episode, but mostly the next episode. However, we tend to, because that is a really small chunk of data to read or write, and that would result in us, for doing on-demand paging, that would result in us doing like 8 disk IOs to get 1 page of data. We actually tend to block the sectors together into larger blocks, and then the OS will do block-based reads and writes. So we're going to do this math instead of with sectors. We can actually just replace sectors with blocks, and the equation is roughly the same. So to figure out how many blocks are in a track, we take the capacity of the track and we divide it by the size of the block, which is 2 to the 12. And that gives us, there are 2 to the power of 5, which of course is 32 blocks per track. So then in order to compute the transfer time, we need to know what percentage of that track are we actually reading or writing. And it's 1 block, so its transfer time is going to be 1 over 32 times the maximum rotational latency. Now this is a common mistake people make, is when you're estimating, the transfer time is how long does it take to rotate the platter through the blocks that you're transferring. So we are reading 1 out of the 32 possible blocks of the track. So that's where the 1 over 32 comes from. That's our fraction of the track we are reading. And we multiply that by the maximum rotational latency because it takes this long to rotate the platter exactly once around, so 360 degrees. And we are going to need to rotate it 1/32 of the way to read that block. So you multiply the fraction by the maximum rotational latency. And a common mistake I see is people will use the average here. Don't use the average. You need to use the maximum here. So then what we're going to do is we're going to take these 3 values and we're going to sum them up. So we get our cost is going to be the average rotational latency, which was 5 milliseconds, plus the average seek time, which was also 5 milliseconds, plus 10 over 32, which is our transfer time. So this is going to give you a value of approximately, roughly, 10.3 milliseconds. Okay. So now we know the cost to do a single I/O operation. We can actually answer the question. And how I'm going to answer the question is by drawing this out kind of the same way we did back in like episode 2 or 3 with looking at context switches and threads. So we're going to start with a process, and we only have one process here. So we'll do P0. And it's going to do 5 milliseconds of compute, and then it does an I/O operation. And then it does 5 milliseconds of compute. And then it does an I/O operation. And we know, having just computed the length of time that I/O operation takes, that this is about 10.3 milliseconds. Okay. Now to figure out the CPU's utilization, we know that, helps if I don't throw my pen. We know that while the disk is performing the I/O operation, so actually moving the motors and doing the read-write, we know that the CPU is going to be idle. And so that means that we are only, so the CPU is in use during these blocks, but not in the other blocks. So what we can do then is we can look at this repeating chunk, and we see that this chunk is about 15.3 milliseconds. So for a 15.3 millisecond period of time, 5 milliseconds is doing actual computation. So this works out to be roughly 1/3 utilization. That's good. So then question 2 asks you, what if you have 2 processes doing the same thing? Well, let's actually draw this out, and hopefully I won't make this too messy. Should probably switch to grid paper. Okay, so here I'm going to do my compute, and then I'm going to do my I/O. Now, while process 0 is doing its I/O, we can have process 1 do its compute. But we also know that the compute is less than the I/O. and we can't have two I/O operations on the same device happening at the same time. So this is going to be just a sleep block. And then we have P1 do its I/O, and then of course we'll have P0 do its compute. And if you draw this out, you kind of see the pattern here. So now I need to find a repeating block to figure out what is the utilization of the CPU. Now the repeating block that I see, and don't worry about the head and tail of this, we're looking at the overall utilization here. The repeating block I see is this one right here. So looking at when one of the processes is doing an I/O operation. So looking at that, we see that the length of time is the length of the I/O operation. So that's going to be our denominator. And then our numerator is going to be the amount of time that we are actually computing during that block, which is 5 milliseconds. So for two processes, we see that the utilization is about half. Now, if you're looking for an extra challenge and you're so bored because, it's mid-July and you've only got a few weeks left and you finished all your other courses early, or you just want to challenge yourself, try to repeat this problem for 3 and 4 processes and see how the utilization changes. And then ask yourself, is it possible for processes as we've described in this problem to achieve 100% utilization? And if it is possible, how many processes are required to achieve that? If it's not possible, tell me what the maximum utilization is. All right. And with that, that is the end of the section on devices. So now, let's have a very brief commercial break.
By the way, I believe in winners and losers, and especially the freedom to fail.
Who? Him? Who? Him? Who? Him? Him? Who? Me?
I don't know. You're not there. Da da da.
No way!
What is love? Baby, don't hurt me.
That's a fun one. All right, so this is the second last topic for CS350, and that is the topic of file systems. So the first thing you have to ask yourself is, what is this whole file systems topic about? Well, this isn't about the disk itself, like how long does it take to actually perform a read or write. At this point, what we're actually interested in is, how do you actually store the data on the disk? Because there's lots of things to consider. Are we storing the data as one contiguous chunk? Because we know that if we store the data as one contiguous chunk, then we're probably going to run into fragmentation issues. And we want to make sure that we are able to actually utilize our disk as best as possible. We don't want to waste any space. So if we're not going to store our files as contiguous chunks, how do we store the files? And then you have to ask yourself, well, even if we did store the files as contiguous chunks, how are we going to be able to keep track of where all the files are actually stored on the disk, so that when I turn my computer off and I turn it back on again, I can actually retrieve those files? And this is actually the job of the file system. So the file system's job is to actually figure out how the data gets stored onto the disk and find ways of storing it that we can actually retrieve it and manipulate it at a later date. So Some terminology, of course. So we have files. Now you know what a file is because you've been using them since forever. They are the persistently named objects that you're storing on your disk. And there's a few interesting things about files that you should know. Files can change size. Now I'm saying it and it's obvious, but it's important to reiterate. Files can change size. I mean, sure, if you download, Endgame from BitTorrent, it's not going to change in size. You download the file, it's that size. Once you've downloaded the whole file, that's the size it will be forever. However, if you're writing like a Word document or writing some code, the file size may grow or it may shrink. And so when we're building a file system, we need to keep it in mind that the actual size of the file can actually change over time. The other thing is that files aren't just their data. There's actually a lot of metadata associated with a file. For example, files have timestamps. We have access controls for things like who is allowed to read and write and execute and so on and so forth. So there's lots of extra things there. Now, the file systems themselves can actually, if you try to find a definition, what is a file system, it's kind of hard because there's different kinds of file systems. So we kind of say that the file system is all of the data structures and algorithms that we use in order to store, retrieve, and access the files. And you can kind of subdivide file systems into 3 different levels. You have the logical file system, which is the high-level API that you are accustomed to. Now, what do I mean by that? So let's go over here. I've got a Finder window open. I think that's what it's called. Sorry, it's kind of funny because I've been using an Apple for about 10 years now and I still don't know what this app is called. I begrudgingly use an Apple. All right, so this is Finder, or if we were using Windows, this would be Explorer, or Linux, it could be Dolphin. But this is how most people interact with the files on their computer. They are able to actually view all of the things that are on their computer. This is my directory of all the lectures, which I need to clean out because I'm running out of hard drive space. So here we have the actual files, and if I want to open one, I just double click on it. And if I want to find information about it, as you can see here, I actually have some of the metadata being displayed. The date it was modified, the size of the file, the kind of file it is, and so on and so forth. So that's fairly standard. But when we're dealing with files, this is usually what we're thinking about. We are thinking about interacting with them through this interface. And if we're not thinking about interacting them through that interface, then if we are actually trying to write to a file in a piece of code, this is the kind of thing that we would be doing. So again, this is C++. I prefer it. Hate me if you want, but it's true. I like C++. So here we go. I've created an output file stream and I want to write to this file blah.txt. So I create the file stream and then I check it to make sure the file is open, and if it is, I just start writing to it. When I'm done writing, I close. That close bit is actually very important, don't forget that. And I'm done. These 2 operations here, whether I was interacting with the file through this little C++ program or whether I was interacting with my files via Finder, they're actually giving us access to the logical file system. Because in this file system here, this API, I don't actually know anything about how the file is stored on disk. Sure, I know what bytes of the file correspond to what data, but I don't know how that data is actually stored on the physical media. Because the physical media has actually been completely abstracted. And that's what the logical file system is it's the abstracted view of your file system. It's simply things being presented to you as how to manage files, how to read and write files, how to access directories, permissions, and so on. It's this high-level API that lets you work with your files without actually knowing anything about how they are stored underneath. For most people, that's the only file system they'll ever access. Underneath the logical file system is an optional level of the file system. I'm going to open Finder back up here, even though this probably won't work for me. So we have underneath the logical file system is an optional layer called the virtual file system. And what the virtual file system lets us do is take multiple file systems, multiple disks, and it presents it to the logical file system in a consistent, uniform way. So for example here, you can see here on my sidebar that under locations, I have this Sangria. Sangria being one of my NASs, my primary one. Oh, it is open. Great. It's weird. I thought its IP address changed. So here you see, this is a different storage. This storage isn't even in this room with me. This storage device that I'm connecting to is attached over the network and is actually below me in the basement. It's cooler down there. And yet, I am accessing this without even realizing that I am connecting to something else. I am accessing this separate storage device, and I'm not even aware it's a separate storage device. It is the virtual file system that takes all of these different disks and presents them to the logical file system as one unified thing. But it's optional because not everybody has multiple devices. The final level of your file system is the physical file system. And it's the physical file system that is dictating how the bytes of data are actually stored on the physical media. And this is not something that we typically interact with. The only time that you would really be interacting with the physical file system is if you were doing some kind of system level formatting. So for example, if you were installing Linux and you have to create partitions, I mean, you could let the installer do it yourself, but I never do. I like to create my own partitions. I like to set up the file systems the way I want. So when you create each partition on the disk, you would say, okay, well, I would like this to be an ext3. Well, ext3 is a physical file system. Just as NTFS, which is Windows journaled file system, that is a physical file system. In Mac, you're going to have HPFS and HPFS Plus if you are using mechanical drives, and you have APFS if you have an SSD and High Sierra or up. So physical file systems, actually, it's funny because when we think of a file system, we are thinking about these named entities, but the named entities are actually the physical file systems. And we can only really interact with them by saying, hey, give me an ext3 partition. Now, if you're sitting there wondering, what's your favorite file system? I had a favorite once upon a time. My favorite used to be RiserFS. So back in the early 2000s, journaled file systems, which we'll talk about in a later episode, weren't really a thing for consumers. And RiserFS was one of the first working journaled file systems offered for Linux. And if you could get it to install, it actually offered superior performance and reliability. And so I loved it. But RiserFS you probably haven't heard of, because it's gone. ext4, ext5, which are journaled file systems now for Linux, have actually incorporated a lot of the concepts of RiserFS into them. One of the reasons why RiserFS kind of isn't a thing anymore is because the creator of it actually murdered his wife and went to prison. If you want to know more, the individual's name is Hans Reiser. Yeah. Crazy, right? I now use ext, obviously. All right. So we're going to start out by taking a little bit of a closer look at the logical file system. This is something that I know most of you are very familiar with, but there's some interesting quirks with it that some people just aren't kind of aware of that are going on, and it's part of the implementation of the operating system. So some of the most basic commands that we have as part of the logical file system is things like open. And you know what that is. If you open a file, you are opening a file. And it means when you open, you usually have to tell open if you're going to read the file or write the file or do both. And there's a reason why you have to specify that. But open does more than just give you this handle or descriptor which lets you write to that file or read from that file at a later date. Open actually does a lot of work. When you open a file, and we will look at this in greater detail later, not today, you are asking the operating system to go to the secondary storage and say, okay, do you have permission to open this file for reading? Do you have permission to open this file for writing? So it's going to check if you have permission to access that file in that way. And if you don't, open will return an exception. And if you do, open will return this unique file identifier, which is also known as a handle or a descriptor. And then what ends up happening is that process now has that file open. But you can actually have the same file open in multiple processes at the same time. As part of the process structure, there is actually an open file descriptor table. And in it, as you open and close files, we will be either adding these descriptors to that process table or removing them. So we keep track of each process, which file it has open, because we're also, as part of this, going to keep track of where in that file that process is right now, because access to file data is sequential, and I'll talk about that in a bit. And then, so open is going to check for permissions. If you have permission, you're going to update the process's file descriptor table to say you now have this file open and you are at position 0 because we haven't done anything with the file yet. And then we're also going to keep track in the kernel of how many processes actually have opened that file right now. So we keep a count. Oh, 6 processes have that file open. And you're actually familiar with this because, and I know so many people don't do this properly anymore, but when you plug in an external storage device, you are supposed to safely eject or properly unmount it before you remove it. There's a variety of reasons why you should do that. But sometimes in Windows, and I've never had this happen in Linux, and I don't know if I've ever had it happen in Mac. I don't usually plug in other things into Mac because it can't write NTFS natively easily. But when you go to do that safe remove, the safe eject in Windows, you think you have closed down all programs which were accessing that file. And so to you, you're like, oh, I can safely eject it now. You hit safe eject and Windows says, no, it's still in use. And you sit there and you're like, but I closed everything. And maybe, and now I don't know the real reason why this happens, but one of the reasons why it might happen is if when those processes closed, they neglected to update that table in the operating system that said how many processes had it open. And so Windows is saying, well, I still detect that a process has that file open, therefore I'm not going to let you eject it because it's not safe to do so. Quirky, eh? Now, so that's what open's going to do. So we're going to make changes to the process structure, but we're also going to make changes to the kernel as well to keep track of the fact that those files are open. Now, what does close do? Close is an interesting thing. So a lot of people neglect to close their files, whether it's you're writing Python code or Perl code or C++ code, you know you're supposed to close the file, but nah, let's do it later. And this actually comes down to, well, another reason why you should say unmount, the reason why you should unmount your disk properly. Writes get cached. So first off, what close is going to do is if you close a file, you are going to update the process's file descriptor table to say this file is no longer open by this process, so we're going to remove it. And then we're going to tell the kernel that one less process has that file open. But one of the other big things that close does is, in some operating systems, writes get cached. And when writes get cached, it means they're being cached in RAM and they won't actually be written to the device until a later time. If you want to make sure that that write actually happens, that last write, you want to make sure that the cached value actually gets flushed out to the device into the proper file. That's why you call close. Close isn't just going to properly shut the file down in the operating system. It's also going to force the last writes to be flushed out to the actual file. So it's really important to call close. I've had this happen, by the way. Like I was writing some Perl code probably 10 or 15 years ago, and I didn't call close. And I was like, why is my last write missing? And my last write was missing because I forgot to close the file. I forgot to flush that last buffered or cached bit of data. So it's very important to call close. And this actually comes into play also with unmounting a file system safely. So sometimes, let's say you're writing a whole bunch, copying a bunch of tiny files. It doesn't usually happen with a big file. It usually happens with teeny files, like really small ones. If you take like a directory of C files and you copy that directory of C files over to its external storage unit, and then you just pull it, you're looking at the little green light, and you're like, oh, the green light on the device has stopped moving. Okay, it's done. I'll just pull it out. And then you take it and you plug that device back into another computer and you notice half the files aren't there. The reason is because those writes were getting cached, and the flush of that cached copying action doesn't actually happen until you safely remove the drive. So it is actually really important that you close the file when you're writing to it, and when you're wanting to take an external storage device off, you should seriously consider safely removing it just in case there is a cached write that hasn't been flushed to disk. Yes, I've had it happen for both of those circumstances. I've had it happen. And even recently, I think I haven't had it happen on this Mac, but on my previous one, probably 5 years ago, I actually had this happen quite a few times where I just pulled the device out thinking, oh, who cares? And yeah, half the data was missing. It's important you do it. So that's open and close. Then we have read, write, and seek. Now, read and write actually do things sequentially, and I'm going to explain that more with an example in a minute. But one of the things you may notice about the API for read and write, and it doesn't matter what language you're doing it in, is that you never actually specify where you want to read from or where you want to write to. So how does the operating system know where in the file your data is supposed to come from or where it's supposed to go? Well, it's because the current position is where in the file is where it's going to go. And the current position is stored in the process's file descriptor table. And when you first open a file, since you haven't done anything, the current position is 0. And then as you request a read or write of so many bytes, you will advance the pointer and such that the next read or write happens from that position. We'll do an example in a minute. Now, sometimes you might actually want to do random writes to a file. Like if I want to read the very last byte of a file and I know my file is like 2 terabytes, I don't want to have to read 2 terabytes of data to get to the last byte of the file. I would like to be able to just magically advance to that position at the end of the file and read those 2 bytes. And that's actually what seek lets you do. So seek is going to manually update the pointer. It doesn't actually touch the file itself. It just updates the pointer so that we can do non-sequential reads and writes. Now, interesting story about the seek operation. And this is true for Linux and Mac OS, so and Unix-based operating systems. I don't know about Windows. Don't know if I've ever used seek in Windows. But seek on Unix-based operating systems does not actually validate that the position you have asked the file pointer to move to is in the file. So if I have a file that contains 1 byte, I can technically seek to byte 3054 and there will be no error. until you do the read or write. So seek doesn't actually validate that the position is real. And you will find out that it's not a valid part of the file when you try to do the subsequent read or write, which will then return an exception. So do be careful using seek, because it will let you go to non-existent positions, because it doesn't check with the file. It's just, think of it as your current position in the file is the byte number you're on, or the address in the file you're at, and seek just adds a number to it or subtracts a number to it. It doesn't actually make sure it's real. So that's how you open and close and read and write and move around in a file. And then we also have the ability to modify the metadata of the file. So that's things like the permissions of the file, the owner of the file, all of those things. So I'm going to go back over to my terminal now, because I'd like to show you something. And let's move my tablet here to the side. It's in my way. All right, so here we have my examples directory, and I can actually learn about all of the different files that I have. So I'm using ls-la, which lists a bunch of the metadata associated with the files in the directory. And what you can see here as the metadata is it has the date associated with it. So this is going to be the creation time. It tells me how big the file is, and it's also telling me this here is the permissions. So there's a bunch of different programs, the little command line things, and there's an API to actually read the file metadata, but also modify the file metadata. For example, if I look at this files.cpp, which is the little C++ program I just showed you, looking at its permissions here, I see that I have read-write permissions. That's me, the owner of the file. And I see that my group has read permission and everybody else only has read permission. Let's suppose I wanted to give everybody, myself, my group that I'm a part of, and everybody else in the world, I want to give them read-write permissions. Well, then there's this magical function called chmod. And again, this is not unique to Mac. This is a Unix program, so you can actually use this in Linux or whatever. And there's various ways to use chmod. You can use it, there's numerical codes to change the permissions, which I find very unreadable. I prefer to use this method. So I want to give my group and others write permissions. So U is for users, group is for group, G is for group, and O is for others. And I want to add write permission. So I do group others plus W files.cpp. I am modifying the metadata of this file. So now you can see when I look at the metadata again, I have actually modified the permissions of this file. Now, this actually brings us to a fun little thing that we can do. So if you've ever had a problem in a course where you're like, but I finished it on time and I can prove it, and the TA is like, okay, we're not going to accept you just showing us the last modify time on your file. They'll only, I mean, if they accept any proof, they might accept things like transaction records from your repo, but we don't accept just this printout of ls-la showing us when you last modified your file. Why don't we allow that? Why don't we permit Linux timestamps as proof that you didn't work on your thing after the deadline? Let me show you why. So let's suppose you had a deadline. And let's suppose that deadline was last month. And you forgot to send your supervisor a paper or a form. And you finally got around to it, or they send you an email and they're like, I haven't gotten this thing from you. And you're like, oh crap, I haven't done it. I totally forgot to do it. And so you've got to think to yourself, how am I going to trick them into thinking I did it when I honestly didn't do it? So you're like, I know, I'll do it right now. And then I'll email them and say, you didn't get it? I sent it a month ago. Here it is again, just in case. I'm sorry there was such an email mix-up. And they'll look at the timestamp and it'll look like you were honest about this. Okay, so here's how you do it. So let's create a file. We'll call it report.txt. And if I show you report.txt, you'll see that the timestamp on it is July 16th at 10:27 a.m. That is like a month after it was actually due. So before I submit this in my email saying, oh, I sent it a month ago, didn't you get it? I need to modify this timestamp. And you can do it with the exact same command I just used to create this damn file. So we're going to do touch, and then we do MT, and now I'm going to specify the new timestamp for the file. So this is July, which I guess is the 7th month. So let's change it to the 6th month. And oh, wait, I don't remember if this is, oh, it's month first. Yes, month, day. So maybe I was working on it in early July. So I did it early. So let's change July 3rd. And I don't want my supervisor to know that I was awake at 3 in the morning. I want them to think that I came into work early and I finished it early in the morning. So what I'm going to do is, well, if I make it a multiple of 5, that looks too fake. So let's say I finish this at 10:13 a.m. That's a good time, right? 10:13 a.m. Okay, there we go. Now let's do an ls-la. And there you go. June 3rd at 10:13 a.m. is the new timestamp for this file. And this is why we don't accept timestamps as proof that you stopped working on your assignment before the deadline, because it is absolutely trivial to modify them. But all of these commands like chmod and touch, they are all a part of the logical file system. They are the abstractions that the operating system is offering you to read and modify files and read and modify the metadata of those files. And yes, every single thing I just did here involved system calls. All of it. All right. So, as I said before, our reads and writes to files are going to be sequential in nature. And when you open a file, the initial position of the file is set to be 0. And that is stored in the process's file descriptor. And then each time you do a read or write, you don't specify where that read or write comes from, starts at, that is. You are going to instead simply say how big the read or write is going to be. And the start position will be the position in the file that is stored in the file descriptor table for your process. So if you do a read and after immediately opening the file of 512 bytes, then you will be reading from byte 0, 512 bytes. And at the end of the read, your file pointer will be at byte 512, such that the next read starts at 512. And the same happens for writing. And that's why seek is so important, because if you want to do some kind of random I/O, you need to be able to move that pointer around. So the little example they give here in the notes is we have some file, and it's a very big file, and I want to read from the file 512 bytes at a time. So what I want to do is I can show you how this file is actually being read. Let's switch over to OneNote here real briefly. Turn my tablet back on. I'm surprised. It probably needs to be charged. Yep, I've got 6% of my battery life on my tablet left. Oh, wow. That's enough. 6% is good. It explains why the orange light's flashing on it, too. So if we have a file, and the file contains A, B, C, D, E, F, G, H, I, J, KL. And let's suppose instead of 512 bytes at a time, we are reading 3 bytes at a time. What that code on that slide is going to do is it reads this. So that's first. And then the second read is this. The third read would read that. And then the fourth read would read that final one. So that is sequential file IO. But that's so boring. I don't want to access my file that way. What if I wanted to read the file backwards 3 bytes at a time? Well, if you look at the example on the following slide, so slide number 6, what you'll see here is we're doing an LSEQ. And what we're doing is we're computing the ith last block of 512 bytes, and then we are reading from that. So what this is going to do is, so red here was reading from the start. And then what we're doing for the other one is we are actually reading JKL first, followed by GHI, and then DEF, and then ABC. So when we use the LSEQ operation, we can actually do things like reading the file backwards so many bytes at a time. And you can only achieve that with seq. And remember that seq will let you move the file pointer to somewhere in the file that doesn't exist, and then without causing an error. But if you try to read or write after that point, you're going to have a really bad time. So be careful. All right. So that's the basic operations. The next thing I want to talk about is directories. So directories, interestingly enough, are also a type of file, but they're actually very special. So from our perspective as a user, every file on our computer is referred to by a long string. I mean, you know that because what we can do is we can go here and you can see pwd. All of the files, so report.txt, its full name is users, Lanortha, Synology Drive, courses, CS350, examples, report.txt. That does two things. Number one, it's a unique identifier for that file, but also it tells me where that file is. But think about this. Do you honestly think that the kernel of your operating systems, which does a lot of file I/O all the time, wants to constantly be referring to files by that long string, which means it's got to do string lookups and string comparisons, and you know that those operations are linear in nature. We don't want to do that. So actually what's interesting about Unix-based file systems is that what we do is we actually assign every file a unique identifying number. And this is called the I number. And inside the kernel of the operating system, we actually don't refer to the file as by its full path, its full name. We only ever refer to the file by its I number. So when you're opening a file, you are actually creating for that process. You are looking up the I number for that file, and then every time you read or write from the file, we're passing the I number around, not the path, because the I number uniquely identifies the file. But then we need some mechanism to map the path, the name of the file, to the actual I number. And how that actually happens is inside of a directory. So we think of directories as, okay, I'm going to open Finder and let's go into, where's the directory I don't care about? Okay, I do care about this directory. I create a folder. I'm going to call this, I'm going to call this by one of my recent project names. So, and then if I want to shove something in there, I will grab it and drag it in there. So we think of it as this container where we shove stuff. It's kind of a bad way of thinking about it. I mean, effectively that's what it does to the user. But what a directory actually is the directory maps the file names to the I numbers. So inside of a directory, and I'll open one for you in a moment, we are actually going to map the name of all of the things in that directory to what I number they are. Now, in a Unix-based operating system, if you open you can actually open a directory inside of something like VI. Unfortunately, it won't show you the I numbers here because you don't want the user to see those I numbers, but you can see what is inside of the directory. So I can actually open this examples directory, and you can actually see in here that it's listing all of the contents, and somewhere this is actually going to map each of these to the I number. Kind of neat, right? And then whenever you actually open a file, we are actually going to be searching the directories to actually find what is the I number for that particular file. And what's interesting is the directory structure actually forms a tree. And this tree, we call it the hierarchical namespace. So the root of the tree is the root of your file system. And then what happens is each of the directories, which are files themselves, and so they are going to have I numbers, but a directory is going to contain the mappings between the names of their contents and their I numbers. So inside of directory bin, which by the way has I number 312, we have two mappings. We have a mapping between private and 654, which is also a directory, and test program and 425, which is a file. Now, what's interesting here is that if you look at that hierarchical namespace tree, you will note that directories can be internal and external nodes. So directories can be internal and they can be leaves, because a directory doesn't have to contain anything. But files, like true files, can actually only be leaves. So you cannot have a file on the inside of this tree. So what happens when you open a file is you give it a path. Let's say you wanted to open foo.misc temp. Then you say open foo.misc temp, and as part of the open process, we are going to traverse this tree. We start at the root, and then we go to foo. And then we're going to open foo by using its I number, and we get the contents of foo. And then we find misc, and we see that misc corresponds to file number 93. So we open 93, and inside of file 93, we find a mapping from temp to 12. And so we finally now have the I number for foo.misc temp as 12. So we traverse this tree to open a file and map the path to the file number. Now, some important things here is that every file actually has to have a unique I number. That's very, very important. If two files have the same I number, that would be a bad thing because they would be overriding each other. What's very interesting is that you can have multiple paths to the same file. So first off, this mapping here between, say, bin and 312, we call that a link, or more specifically, we call it a hard link, which is different from a soft link or a symlink, which we no longer talk about in this course, by the way. But this link is the actual mapping between the name and the I number. So when you create a file, you are actually opening the directory that the file is going to live in, and you are adding an association. You are adding a hard link between the name of the file and the I number. You'll get the I number from the physical file system, which we'll talk about at a later date, how that works and how they're assigned. So that's creating a hard link. You can make multiple hard links to the same file. You can have multiple paths to the same file. So if you look at this here, we've actually done just that. So using the link command, which creates additional hard links, I have actually created a hard link docs.a.txt, so I can access file 147 by opening docs.a.txt. That will return file 147. But I added an additional hard link from foo.mya to 147. So I could also open file 147 by calling foo.mya. Hard links can be created via the link command, but they should never be created for directories. And there is a very good reason for that. So we don't permit hard links with directories. Now, hopefully I've got just enough battery life to do this. See what it says I have left. 5%. So let's suppose that this is directory foo. And directory foo is 87. And inside directory foo, I have directory bar. And directory bar is going to be, let's say 51. And then inside of bar, which is 51, let's say I have this.txt, and it's going to be 101, and then I have a link to www, which is 87. So that is, here's foo, and foo has a link to bar. Inside of bar, I have the file this, and then I also have a link back to foo called www. Do you see the problem I just created? How many valid path names are there for this.txt? Well, let's write out some of those path names. We have foo bar this. We have foo bar www bar this. I have foo bar www bar www bar this, and so on and so forth. I've created a loop, and that loop actually ended up creating an infinite number of paths that all map to the same file. That cycle that we created can be problematic. Imagine you're on a Mac and we permitted this kind of hard link, and you tell Mac, show me all my files. When does it finish? Never finishes. So in order to prevent cycles, most systems will not permit you to create links to multiple hard links to directories. You can only usually create multiple hard links to a file. Now, it's not to say you couldn't build your system to just detect this and prevent it, but if you remember your 341, how hard is it to detect a cycle? Remember, you've got hundreds of thousands of files here. All right. So we can create multiple hard links to a file. We actually keep track as part of the file system's metadata, or the file's metadata, we actually keep track of how many hard links to each file there are, because we need to know at what point is there no path to that file. Because if there's no path to the file, then we should delete the file, because there's no way to access it anymore. There's no mapping from a text path to that file number. When there's no mappings, then get rid of it. So in order to get rid of a hard link, we have this unlink command. When you unlink, you are removing from a directory the mapping between the name and the I number. And when there are no longer any hard links to a file, that should signal to your system it is now time to delete the file. Okay. So that is actually the end of discussion on logical file systems. So logical file systems are all of those abstract API functions for directories, for files, that don't actually tell you about how data is stored on the disk. I mean, this here, this hierarchical namespace, this tells me the overall structure of how I've organized my data, but really it didn't tell me how the data was stored on the disk. This is just how I map my file names to their I numbers, which I never even see as a user. So this is all very abstract. So I'm going to call it here for today. And in our next episode, we are actually going to discuss the virtual file system, which is how do we combine multiple file systems together as one. And then we're going to start talking about the physical file system. So we will see you next week for episode 21.
thought today was a play day. Where are you, man?
I'll be there in 10 minutes.
All right.
Great. All right. Look busy. Don't sign anything while I'm gone. Whenever Steve and I can, we slip away from the office and talk about the future of technology. Just getting away from our desk makes us feel like kids again. Hey, play day, play day. Hey.
Tonight we gonna make it happen. Tonight we'll put all other things
Push me.
Ah, it's always about you. It's always about you.
some fraction. We go for those pleasures in the night. I want to love you, feel you, wrap myself around you. I want to squeeze you, please you. I just can't get enough. And if you move real slow, I let it go. I'm so excited.
It's amazing to think of all the things we'll be able to do with the technological breakthroughs that are just around the corner. Hey, Steve.
How you doing?
Thanks for meeting me here.
Pleasure, pleasure. We want to go and get a couple things
Yeah,
while we're
let's
out?
grab some stuff.
I'll be ripe on Tuesday. I'm ripe right now.
Hey, pal, check out this New York produce. Here, squeeze this.
You know what Tiger Woods and I have in common?
Not your golf swing, that I guarantee you.
Well, check this out. Just like Tiger.
That's not such a big deal.
But I think you're jealous.
I'm not.
I think you are.
I'm not. As a matter of fact, just step right back here and take a look at that.
Oh, my goodness.
Isn't that great?
I forgot my wallet again.
At least fumble around a while longer. That excuse is getting old. All right, I'll get it. I'll get it. See here, I got the smart card. I'm ready to roll, man.
And I got some coupons. I'm going to save you a lot of money here. Just a couple of those.
Mr. Coupon. All right.
It's my secretary. Let me zoom out.
Oh, Mr. Gates, did you forget the interviews you have all over campus? Well, don't worry, I got it covered. We'll go to Plan B.
Thanks. I've still got a few errands to do.
Would there be anything else?
Just this book. It's for a friend.
Oh, hello, Mr. Gates. Just be a moment. Here you go.
Did you ever find that lost sweater of mine?
No, but we're still looking.
Well, it really was one of my favorites, so keep looking.
Okay.
See you next week. We look to the future when innovation will give us the time to do the things we really love.
Oh, I love your new sweater. Time for your next meeting?